Hello, my name is Mason. I'm a PhD student in Professor D'Amico's lab. I'm in my 5th year of my PhD. I'm a NSTGRO fellow, and I do a lot of work on this mission called VISORS, which is an NSF-funded mission. Joining me here is Toby, who's another PhD student in our lab, and he's going to take over halfway through the presentation. We've done a little bit of a divide of like the relative orbit design and like the flight software writing. And so this has been a project that's been going on in our lab for a long time. There's been a lot of students and postdocs who have touched this, both from Stanford and from a bunch of other universities. So I'll go start off with a quick video that just shows broadly the operations of the VISORS mission. If I have mouse control, there it is. Okay. Bigger? No. VISORS is a spacecraft formation consisting of two 6U CubeSats, and it does has some exciting science goals. So this will show you an introduction of the general operations of the spacecraft as they're operating in formation, and then I'll go more specifically into basically everything you'll see in this short intro video. This was made by Sam in our lab using SD code. So, great. Nope. Okay, yeah. So VISORS is a multi-university / institution collaboration. So we have multiple universities, as well as NASA, NSF, that have come together to work on the hardware and software to make this a viable flight project. VISORS is supposed to launch any day now, they say. Hopefully we'll get it in the air soon, and we'll have a nice demonstration from Stanford of both some able to obtain some new science goals and do some demonstrations of algorithms in orbit for the first time. So I'm going to first take you through the mission overview, so what the mission is going to accomplish, the different modes that the mission will go through, and what is relevant to consider in each mode. And through that, I'll be talking about the guidance and control algorithms that are at play in each phase. Then Toby will take you through some of the flight software, how we design the flight software to do coordinated autonomy of two spacecraft that are operating in sync. I'm sure you guys are all very familiar by now because you're at the end of the quarter of the relative flight dynamics class, but there's a lot that goes into making a suitable flight system. So VISORS is a distributed telescope. So what the goal of VISORS is to have a optic spacecraft and a detector spacecraft form a distributed telescope in space, so you can get unprecedented resolution of areas of the sun, and will create new images of the sun that we have been previously unable to do. If you heard of the Probe 3 mission, which was launched recently, I think it's a very similar concept. This is a low Earth near circular orbit, absolute orbit design, so it's a bit different from the Probe 3 orbit. But we are going to be attempting to image the sun using this distributed formation. And the distributed formation allows us the benefit of, rather than setting up a gigantic telescope with a 40-meter long focal length, we can send up two spacecraft and have them align in space and take measurements, which drastically cuts down the cost of like sending a giant object into space. But of course, it ups the relative accuracy and control that we need to be able to make this an actual usable measurement. and make these measurements useful for science on the Earth. This is an overview which, if you're implementing projects, you probably have taken from some of these as inspiration of similar CubeSat or larger sized formation flying missions that have accomplished similar goals. Professor D'Amico was involved in several of these, but using similar techniques from these and some heritage flight algorithms, we will help to achieve VISORS science goals, which are driven by maintaining the optical formation to make the telescope able to image the sun. So this gives us primarily some geometric constraints on where the spacecraft can be oriented in the RTN frame and as they're facing the sun. So for our 40-meter distributed telescope, we have a constraint on the alignment of the spacecraft. There's like a 90 arcsecond alignment window that they have to be within at a range of 40 meters. In order to keep the resolution and to keep the image from blurring, the spacecraft have to be very still in this time period. So we have to position ourselves very accurately with very little relative velocity, and we make choices about the relative orbit based on these design considerations. This is a lower fidelity attempt. So this is not a mission where we're attempting to achieve hundreds of images, lots of success. This is like a probabilistic. We will sometimes achieve a observation that is a successful imaging of the sun. We are aiming, the mission goal is to obtain one good image, one usable image. With a 20% success rate on each imaging attempt, that is a 99% chance overall if you take 20 consecutive chances. If you're 20% likelihood, you will have a 99% chance of obtaining at least one usable observation. If you have 10 observations, you'll have 90% chance. So the spacecraft are 6U CubeSats, so they're not super big, they're not super highly engineered. This leaves some considerations on what we're able to achieve at any given moment with the spacecraft. Some of the more relevant restrictions are due to the actuators on the spacecraft. These are impulsively controlled spacecraft. There's 6 impulsive thrusters aboard each spacecraft oriented all perpendicular to each other. There is reaction wheels for attitude control and desaturation, and there is a crosslink constantly speaking between the spacecraft. The crosslink we have to operate in range, so the spacecraft have to not only stay in range to do differential measurements and communicate with their guidance. The spacecraft have to make all their control and guidance plans abide by the restrictions of the actuator hardware. So this is the general ConOps of the VISORS mission. So it's divided into a few operating modes. So I'll focus mostly on the autonomous modes for this discussion. So standby is our safe orbit. We're sitting in standby. There's a large separation between the spacecraft where they can hang out, not expecting any random perturbation events to bring us into a potentially dangerous situation with the spacecraft where they'll crash together, and we're not expecting them to drift apart. So we'll do station keeping to keep them from getting too close or too far in a standby orbit, which is a fairly large separation. Not fairly large, fairly small. It's about 200 meters in RN separation at all times in standby. So this allows us to do things like downlink our imagery when we take observations. The spacecraft will stay in standby for about 2 weeks at a time before, between intermittent observations. Observations take, to go in and take an observation and come back out to standby takes a few days. The transfer orbit is what will get us from our standby orbit to our science orbit. The science orbit is what we described when we're doing the specifications for the positioning and the relative speeds of the spacecraft. That is prescribed by our science orbit. The spacecraft have to be much closer than they do in standby to make those observations. So we want to make sure that they can be generally safe that entire time. So the transfer will safely take the spacecraft into the science orbit, and during the science orbit, they will be controlled to get to probabilistically take observations as best they can. At any given time, an escape might happen. Not any given time, a time where a contingency event happens, the spacecraft detect on board a passive safety violation, an escape can occur, which will rapidly separate the spacecraft so that they can be diagnosed with the problem. The problem can be diagnosed on the ground, and we can safely take back control, in which case the spacecraft will escape, and they'll basically go inert, and we'll wait for a ground-in-the-loop intervention to get them back working. So I'm going to take you mode by mode to see, or first I'm going to show you some algorithms that are applied throughout the project, and then we'll break out into each mode and see what they actually do. So the major control algorithms used for this project are, one is closed form solutions. You've probably covered this in lecture. So these are ROE-based closed form solutions for optimal control of the spacecraft relative state. These solutions are nice. They can be computed very quickly on board. They are limited in the sense that you need a certain length of orbit horizon in order to compute them. So you nominally need at least like 1.5 orbits in the future to do an arbitrary reconfiguration of your ROE state with these closed form solutions. So they're useful in standby, doing station keeping, and in transfer, doing our large reconfiguration from the standby orbit to the science orbit. For the science orbit, where we might need control on a much shorter time span, we have two algorithms available. So there's a convex optimization-based algorithm. So this uses a second-order cone program to find optimal maneuver times, followed by a quadratic program to find optimal maneuver sizes at these times. And this allows us to do a very quick reconfiguration of the spacecraft formation in a shorter time horizon than the closed form solution. A fallback for that is a Tikhonov regularized least squares solution. So this will attempt to minimize the error for a set of impulses to solve the reconfiguration, but it is not guaranteed optimal. But it is analytical. So this is an option where you have a short time horizon and your convex solver is in trouble for some reason. You can always rely on this as a backup to get you some solution to minimize the error. Then for escape, there is a algorithm that is a single impulse that can be actuated at any time on the spacecraft, planned and actuated at any time on the spacecraft. And the object of this is not to go to a specific ROE state. Like each other objective is to go to a specific ROE state reconfiguration. Safety and escape is just to get us to a safe configuration. It doesn't matter explicitly what it is. Okay, so considerations for the standby relative orbit. So I've broken up on top the relative orbital elements and how they relate to the RTN motion in a near circular low Earth orbit. So I don't know if Professor D'Amico's covered this in class, the concept of eccentricity inclination vector separation. Has he talked about this? Okay, great. Yeah, so this is a nice relative orbit design tool where we can control basically what the shape of our RN motion will be using our relative orbit elements. And we can use this to great effect to separate the spacecraft. So you'll see on the image on the right there, I have eccentricity vector and inclination vector parallel. This leads to a very easily interactable RN motion where you're basically an ellipse with your semi-major and semi-minor axes set by your eccentricity and inclination vector lengths. A terrible case for this type of application would be a perpendicular eccentricity inclination vector because you have a degenerate ellipse solution which basically guarantees that the two spacecraft will pass through each other in the RN direction. We consider passive safety in the RN plane, especially because the along track direction is very subject to perturbation effects and uncertainty due to atmospheric drag effects. So for long-term safety, when we're designing our standby orbit and all passive safe applications, we look at just the RN safety. But yeah, so this, you don't strictly need perpendicular or parallel states to know if an orbit is safe or unsafe, but the perpendicular states do give a very easy to diagnose and design measure of separation for the spacecraft operating in standby mode. And so we have our easy 200 meter by 200 meter relative motion in the RN plane at our standby orbit. So nominally we sit in our standby orbit, but of course we're encountering orbital perturbation effects that'll affect our spacecraft and will deteriorate this solution over time. So they won't stay perfectly EI vector separated over time. In the relative spacecraft states, you particularly see these perturbation effects. We were looking previously at the eccentricity and inclination vector states. So this is the perturbation effects on the eccentricity and inclination vector states. The long terms, like the averaged effect on the mean relative orbit elements for the eccentricity vector due to primarily Earth oblateness effects. The most significant you'll see at low Earth orbit is due to these Earth oblateness effects, J2, is a rotation of the eccentricity of the relative eccentricity vector. So it'll spin, and the direction will be, I think, depending on whether you're above or below critical inclination. The inclination vector, on the other hand, the effect you'll see is on the long-term perturbation effect you'll see is only on the y component. And you'll see that the effect is related to the difference in inclination between the spacecraft. That's delta I at the end of the diy dt. And if you refer back to the definition of the relative orbit elements, the relative inclination vector x component is just the difference in inclination between the spacecraft. So the larger the x component of your relative inclination vector, the larger the perturbation effects will be on your relative inclination vector. For this reason, we choose to have a nominally vertical eccentricity inclination vector so that the effects of perturbations are minimized on the inclination vector when we're in standby. So we want that long term, don't want to be constantly going back to fix the scenario. And what this actually looks like when we're implementing a station keeping algorithm is a check on basically bands of ROE space on what is tolerable and not tolerable, and when we decide to reconfigure. So one thing we look at is the eccentricity vector. As I mentioned before, you'll see a rotation. So we basically can bound an angle or a phase around the relative eccentricity vector. When it violates that phase, you just snap back to the negative of that phase. So the blue will be the natural motion, and the red will be the correction. And you'll snap back, and then you'll just pass back through. You can get a nice cycle of just hitting the boundary, snap back, hit the boundary, snap back. The same can be said for the relative semi-major axis and the relative mean longitude states, where you will drift due to your direction. One spacecraft will be above the other, and due to Keplerian effects, one will lead and one will lag. So when one leads and one lags, you just will swap the direction lightly so that they drift back towards center to eliminate the delta lambda drift. And the relative inclination vector, the perturbation effects due to our choice of the standby orbit are not very significant. So any changes we do can basically just cover that when we do reconfiguration for the other relative orbital states. And then this will be what we actually see in practice. So when we model in simulation our VISORS spacecraft, this is showing the eccentricity vector correction and the relative semi-major axis correction. And what we see is a case that is dominated by differential drag effects. So the drift in the relative mean longitude is the more significant perturbation effect for this set of spacecraft for the parameters that they currently have, their current mass based on their fuel capacity and their average orientation. So the perturbation effect of the drag is to roughly to increase the relative semi-major axis or decrease the relative semi-major axis depending on the sign of the relativistic coefficient. So you get that rather than like a straight drift, you'll get a parabolic motion in the delta A, delta lambda plane. And so this ends up being a more significant perturbation effect in our orbit. So we correct for that more often than our eccentricity vector, and in all cases, basically. So when we violate a boundary, we'll just reset all the states back to their opposite side. For the science mode, so the goal of the science mode is to achieve a specific positioning with the spacecraft formation with respect to each other and the sun. So what we try to do is align this beta angle. So the beta angle is the angle in the TN plane where the spacecraft that points inertially to the sun. And what we attempt to do is to have minimized our relative motion in the RTN frame and have no acceleration in the RTN frame. So we can geometrically take these conditions to generate a set of RTN states. So that's the two lines on the right. So these are RTN Cartesian position and velocity states that yield this separation with the beta angle that aligns the two spacecraft. And using the ROE RTN state transitions, so you have a linear transformation between ROE and RTN states, you can map these states into ROE states. So when we want to design a science orbit, we can take a simple function of our ROE states and design an ROE orbit that will allow us to take these observations. And that's what we target when we transfer. So the beta angle affects our absolute orbit affects what we're able to observe and how safe our formation is when we're doing that observation. So the shape of the relative orbit will be fairly influenced by what this angle is, and it sets bounds on what we can choose for the beta angle, so that our Rn separation doesn't fall below a minimum when we're taking our science measurements. In our science mode, the nominal separation in the Rn plane for a favorable orbit, if we get launched into a favorable local time of the ascending node, is about like 25 meters. In a unfortunate local time of the ascending node, the separation in the Rn plane to achieve this beta angle can go down to 0. So we basically have a range of acceptable, from this we see there's basically a range of acceptable LTANs for a specific altitude that we're launched at that allows us to meet our science objectives. And so we need to be launched into this window from our launch provider in order to have a usable science orbit. If not, then the science orbit will be necessarily unsafe. You have a question?
Yeah. Could you possibly go back to the standby stage keeping?
Yeah, of course. This one is.
Yeah. Could you explain like how you're like determining when you're going to make a maneuver? Because it seems like there are some periods like in the delta A, delta lambda plot where you're making maneuvers when you're like kind of far away from the dead band.
Yeah. It's using a propagated trajectory, not like the actual violation. It's checking 1 or 2 orbits in the future to see if you're violating the band. And if you're expected to violate the band, then it'll do it before you violate the band.
So was it kind of like heuristically determined like that, like, you know, maneuvering at these specific times tends to like decrease the amount of delta V used for stage keeping or something?
No, not really. It's basically just the bound is like a bound that we never want to violate. So like once we anticipate that we are going to violate it, we make our correction decision just based on like the immediate knowledge that it will be violated. The correction frequency is, I'm not 100% sure. I think this is over 1 week, and it corrected like more than once a day. So it is due to that along track drift effect. It is fairly frequent that it needs to adjust. In a lesser drag environment, so if we're launched into a higher altitude, the range of altitude for this mission is potentially like 500 to 600 kilometers, or maybe lower if we're unlucky. The drag environment gets less significant, so we can have less domination effects from the drag that make this reconfiguration happen all the time, and then we would likely see more delta E dominated cases. Okay. Okay, transfer mode. So we have to go from a nominal standby orbit to our computed science orbit. This entails, one thing I don't think I covered was from the design of the science orbit, we can see that our eccentricity inclination vectors are aligned. They're eccentricity inclination vector parallel in this solution. So this is a very, very fortunate configuration that this allows us to guarantee passive safety in the relative orbit design for the science mode. And so when we're doing our transfer, we are transferring from our standby orbit, which is passive safe, to our science orbit, which is passive safe. However, like a arbitrary transition between these states is not passive safe. Like if you did just your eccentricity vector and then your inclination vector after, they would basically go perpendicular at some point in between, and then you'd completely destroy your Rn separation. So the way we address the transfer to hold the passive safety over the entire window and to make sure the actuators are not saturating is to basically break it up into a series of waypoints. So we just basically take a step in the direction, we break it into steps along the direction of the desired reconfiguration with a fixed step size that is tuned to avoid saturating the reaction wheels. Due to the frequent maneuvers that are done, the reaction wheels can build up, or the spacecraft will build up excess momentum that the reaction wheels have to mitigate. If we are maneuvering too fast, the reaction wheels will saturate and we will lose our attitude authority. So this is spaced mainly to avoid that case. So we did this based on a trial or iterations in simulation to see what was avoiding saturating our reaction wheels. And this is using the closed form solver because we have a long reconfiguration window. This typically takes, I think, about 4 or 5 steps of 1.5 orbits each. And then we'll typically arrive from our departure. We'll arrive in like 10 or 11 orbits usually. And then there's a tolerance around the final science orbit where we'll switch to our our convex optimization-based solver that'll compute the actual control to get to the science state. So it's a rough control that transfers to a finer control. And so this is showing that trajectory of the eccentricity and inclination vectors in simulation for our spacecraft, as well as the separation of the, as well as a plot of the separation between the spacecraft. You'll see the eccentricity and inclination vectors. If you've been implementing in your problem sets your impulsive control of your spacecraft, you'd expect a change in the eccentricity and inclination vectors, or any ROE state basically, from an impulse to be like a straight line. Like you're instantaneously changing your eccentricity and inclination vectors. However, you'll see here that these are more like bendy. They're like wavy as they go. The reason for that is I mentioned briefly before that there's limits on our impulsive actuators as well as our reaction wheels. So we're able to output like a max of like a 2 millimeter per second bit over some refill time for the spacecraft, which is about like 46 seconds. So every 46 seconds, one spacecraft can output only a 2 millimeter per second bit. So running after all of our control algorithms, there's one more algorithm, which I'll show later, which just distributes that single large impulse. So instead of the like sharp transitions between the states, into a series of smaller impulses that'll abide by the control limitation. And this is showing the separation between the spacecraft as we go from our 200-meter orbit down to our in RN separation down to our like 25-meter separation. And we have a like safety warning threshold of a 5-meter separation between the spacecraft. That's done by the probabilistic conjunction assessment algorithm, which is shown later. Okay, and then this to show the RTN motion of the spacecraft within one science campaign, where we go from standby to science and back. You can see that the spacecraft align in the B-plane direction. I think is a neat plot showing the RN and RT motion broken out separately, and you can see the separation is safely maintained throughout the entire reconfiguration. So this is the maneuver constraint satisfaction algorithm. There's one more mode to cover, the escape mode, but I'll cover that after this because this is relevant to all the control you've seen so far. So what we basically have to do is ensure that our original plans, which will come from the closed form solution or the optimization-based solvers, will abide by this maximum impulse bit. This can be reconstrued as a linear program where we just seek to recreate the exact same dynamics. So there's a few constraints on size that just make sure that we have the safe sizing of the maneuvers, and then there's a constraint in our dynamics where we're trying to basically just recreate the exact same net effect of a reconfiguration on the orbital elements using a state transition matrix. So this will just take the original maneuvers. You'll get out a set of like 3 in-plane, 1 out-of-plane maneuvers. Each one of those can be broken up into a discretized time series, and over that time series you solve a set of impulses that'll recreate the effect of the original impulse subject to linearized dynamics. And then if these decompositions run into each other, you just combine those maneuvers separately and then resolve. Yes?
Why like the long inequality there is like
this one is
the middle one. Yeah.
Yeah. Yeah, go ahead.
Is that kind of like approximation of like L2 norm or like?
That is just that all. Yeah, it's like an L1 norm of all of like the positive direction firing thrusters. So each thruster, like we consider like each direction firing positive only. So like you just have if it was positive or negative, you just count them both as a positive contribution to the net total. So it's like an L1 norm of all the thrust has to be lower than the 2 millimeter per second output. Okay, so the spacecraft are in this close orbit where they are not supposed to touch each other nominally. They're supposed to get close, but if they touch each other, they could break. They could create space junk. We want to avoid that. So at all times and in all operating modes in the autonomous scheme, there is an ongoing passive safety violation detection. So what this will do is it'll on board, we estimate the spacecraft states, of course. I have not really covered estimation navigation, but if you saw Sam's lecture earlier, we use differential GNSS in digital to have very, very good position and velocity accuracy of the spacecraft. So what we'll do is we'll take that state estimate and covariance, and we will propagate the effects on the spacecraft, on the spacecraft mean estimates separately, and then we'll propagate the ROE covariance using linearized covariance propagation with a similarity transform over time to create a bubble in space at future times where the expected location of the deputy is relative to the chief. So we'll basically create like a 99% confidence interval, like a 3 sigma confidence interval on the Cartesian position of one spacecraft relative to the other one. And if this bubble is further away than our minimum distance, then we're fine. If the bubble is closer than our minimum distance threshold, then we have a passive safety violation, in which case there is a chance that there's a chance that one of the spacecraft, the bubble that is 99% likely to contain it, is violating our minimum separation guarantee, and this will trigger an escape response between the spacecraft. So when the spacecraft want to escape, I mentioned before that you can do eccentricity inclination vector separation, and it's a very easy analytical condition, but it's not like the only condition you need to do that guarantees RN separation between the spacecraft. What we want in an escape solution is something that will rapidly separate the spacecraft. So we will want to introduce an along track drift between the spacecraft so that it can separate in the long term. And over a window in which they're separating, we want to maintain safe RN separation. So for that, we will attempt to solve for an impulse that will get us into a safe configuration with a minimum specified along track drift condition, or along track drift rate that's fixed by the relative semi-major axis. So we'll, from our control input matrix on the ROEs with an impulsive velocity, we can solve directly a relative semi-major axis difference. We can lengthen or shorten the relative inclination vector to be longer than our minimum separation, and then we can solve exactly a relative eccentricity vector we can solve exactly an impulse in the r direction for the eccentricity vector that will make our minimum distance be no less than it was at the moment in which you actuated the maneuver to a relative orbit that is like centered at the origin shifted by an amount of the relative semi-major axis change. And basically what you can do is instantaneously circularize the relative orbit and maintain a safe RN separation without with a guaranteed along track drift. So this can be done for any location in the maneuver, so any phase, any mean latitude that is not already violating separation. So that's why you have to pair it with a predictive safety violation algorithm. So if you have a prior warning that you're violating and you're not instantaneously violating, then you can always generate a single impulse solution that will get you to long-term safety. However, this algorithm is also subject to the splitting algorithm that needs to make sure that we are satisfying maneuver constraints. So even if you plan instantaneously for a very large maneuver, it may still take you a few refill cycles to actually actuate it, in which case safety could be compromised, and that's part of why the vigilance in the long-term lookout is important. I think this might be, I was just showing a solution where the blue orbit previously undergoes an impulse, and you can see in the RTN space and the eccentricity inclination vector space what the change in the states is that gives us a safely separated RN separation. If you select your current location as the minimum separation, you basically turn that hyperbola solution that I showed in a previous slide into a single line, so you can solve exactly a single impulse that makes you no worse than you were before. And now I will turn it over to Toby now, if Toby is ready to go.
I believe so.
Okay, awesome.
Toby section. If I turn on my camera, does it show up anywhere useful or no?
I wouldn't turn it on, Toby. Don't worry. I have you on my desktop here. Should I give them back control of this?
No. I can just not.
But you're gonna have to mouse through, so you're gonna have to click through.
Oh yeah, sure. I can do that.
Thank you.
So Mason, you can drive the slides for me?
Yes.
Okay, cool.
Hold on, why is it
Thanks.
not full screen?
Hi, everyone. Sorry to be joining you from remotely. I fell ill over the weekend, so I'm presenting from home today. The second half of this presentation, I wanted to just give a sense of what our flight software looks like. Since Professor D'Amico gave a direction to make these kind of tutorial-like, I mean, this is not literally a tutorial, but the goal here is to give you guys a sense of what does the rest of the process actually look like if you want to take algorithms for distributed space systems and turn them into real flight software that you would fly on a spacecraft. What's involved in that? I can't see any of you guys, but if anyone has questions at any time, feel free to I guess get Mason's attention or something, and then he can interrupt me, or you can shout loud enough. Okay, next slide. So just to give an overview of what the VISORS GNC flight software actually is, what it looks like. At the end of the day, the thing that we're making, the thing that we're delivering is a piece of flight software that gets compiled to a shared library, just like a library that you'd load into another piece of software on your computer. So it's literally a file, and it runs in a Linux environment, and it's written from a bunch of C++ files. Next slide. So our flight software runs in the context of another piece of software written by people at Georgia Tech. So we have a team of collaborators at Georgia Tech that wrote software that interfaces with the spacecraft bus platform that we're using. And our software kind of gets used by their software as a library for running all the GNC algorithms. So the Georgia Tech software handles all of the input and output for us with external subsystems. And then we handle all the operation of the GNC algorithms that are actually needed to control those subsystems. So some of the hardware subsystems on VISORS that we care about at the end of the day are our GPS receivers, the ADCS system that's built into the spacecraft bus, crosslink that allows us to communicate back and forth between our two spacecraft, of course, the propulsion systems so that we can maneuver, and we also have an auxiliary sensing mechanism, which is the laser rangefinder that is not a default critical part of our GNC algorithms, but is being flown kind of experimentally, and we'll do some sensor fusion with that. And then, of course, communication with the ground. Next slide. So in terms of the way that our flight software actually interfaces with the Georgia Tech software, we give them a header file. If you guys have taken like CS106B or anything like that, you guys know you make a header file in C or C++, and you just define a bunch of functions there. And they take that header file, write code that calls the functions that we define, and then link against our library, and the code gets linked together. And so we give them a bunch of functions that they can call to basically initialize our state of GNC algorithms and then give us inputs. So they'll call functions on us to say, hey, here's an attitude message from the bus. Here's a GPS message from a GPS receiver. Here's a message we received on the crosslink from the other spacecraft. And then we handle those inside those functions. In the other direction, the host software from Georgia Tech also gives us a bunch of functions that they want us to call when we have outputs that we want to give them. So if we want to output a maneuver to them, we'll call a function that they define. And when they initialize us, they give us function pointers to all of those functions. So we can, kind of like a function handle in MATLAB, if you used that, so we can call our outputs back to them. Next slide. So just to get real concrete, because I think sometimes getting concrete and into the weeds just a little bit helps to give a sense of the way something actually works. I've just copied here our input functions from gnc.h, the header file that we actually deliver to the people we work with at Georgia Tech. And you can see some of the functions that we define for them to call on us. And so there's nothing too crazy going on. They just initialize what we call a GNC object, and then all of these other functions they can call to pass data pointers into us and such that we'll then operate on before returning to them. Next slide. Other direction, we output actually quite a few things to them. Obviously maneuvers, we want to be able to maneuver, but we also take charge of operating some of the other subsystems on the spacecraft, like determining when to power on and off star tracker, one of the star trackers on the bus, the laser rangefinder, logging our telemetry, sending messages to the other spacecraft. One interesting thing that I'll call out here that is maybe a kind of unusual way of doing interfacing for software is we output these things called ticks. So about halfway down the list there on the left, you can see we have this function called outTick. And this is basically a request to be called back at a later time by the host software. So for example, if we plan a bunch of maneuvers and we don't want to do any maneuver right now, but after running one of our control solvers, we know we're going to want to maneuver in, let's say, 18 seconds. We can output a tick saying, hey, Georgia Tech software, please call us back in 18 seconds. And then they'll just come back and call an input function on us saying, hey, it's 18 seconds later. You asked us to call you back. Here you are. Do whatever you want. And then at that time, we can actually output a maneuver. We chose to do this early on rather than, for example, using a more explicit like maneuver outputting interface where we say, for example, tell the Georgia Tech software that we want to do a maneuver in 18 seconds. Right? You could imagine that as an alternative interface. It's like we output a maneuver plan saying, hey, please in 18 seconds do this maneuver. And we chose to use this tick interface instead of that for two reasons. One, it's less work for the DT team. So they don't have to deal with interfacing, keeping track of what maneuvers we've told them to do. They can just respond instantaneously when we tell them to do a maneuver. And so that's less onus on them and also less likely that something will go wrong if, we interpret the interface slightly differently. So simpler interfaces are better for distributed teams. And then the other reason is we may want to change our mind of what maneuvers we're doing. And so we'd have to add some sort of interface to say, oh, please cancel a maneuver we previously told you to do, et cetera. So this tick type interface lets us manage kind of the flow of time very explicitly in the software and just give instantaneous outputs when we want the Georgia Tech software to do something. Next slide. Okay, so to give a view of sort of what's on the inside of the GNC software, broadly, we have come to think of it as structured in three kind of main subsystems inside GNC: navigation, control, and then safety, kind of collision detection monitoring component. And Mason, you can go next slide. I always find it amusing to see kind of Conway's law pop up. Conway's law is something that is often quoted in software engineering, which is that organizations kind of ship the structure of their team in the structure of the software that they build. So the VISORS flight software has largely been built by 4 of us in the Space Rendezvous Lab over the last few years. And we've kind of settled into having this structure in the code of like each of us kind of owns this piece and works on this piece. So navigation is largely the purview of Sam Lowe. Control was largely built up by Tommaso Gufanti, a postdoc who's now moved on. And Mason largely spent a lot of his time focusing on the collision detection and avoidance parts of the software. And so I always just find it amusing to see. And I focus a lot on the integration, so kind of the top level GNC part. This will often happen when you build software in teams. Next slide. Just to give a little more look on the way we structure our code. So when we built the flight software, we actually have it in a Git repo with some other flight software projects that our lab maintains. And so we share some of the code pieces between these different projects. And so if we make bug fixes in one of them, all the projects can benefit from them, and so on. And so the internals of the navigation component use a lot of code from Digital, which is a library that I think Sam Lowe presented on a couple weeks ago for high precision differential GNSS navigation. And then as well as our control components use a lot of closed form and numeric control solvers that we share with some other flight software projects. So those are broken out into a separate library, as well as an external library called ECOS that we use for second order cone problem solving, kind of a lightweight convex optimization solver. And then those also all depend and all kind of use some common shared code throughout our software repository that all of our projects use. Next slide. All in all, the VISORS flight software is about 18.5 thousand lines of code, C++ code. This is just like, literally counting the lines of code in the source files. This may be slightly underestimate, but not too big. I actually, on second thought, I don't know if I counted the header files on this, but just to give a sense, it's not that big. We try to keep the code pretty small, and we don't use, whenever we're using external libraries, external code, we'll kind of audit the pieces that we want of them and bring those in. And so we can keep a pretty tight grasp on what code we're actually putting into the flight software. Next slide. So I thought it would be interesting to share a little of how we literally turn sort of modules or components, the kinds of things we might talk about at a high level in like control systems design, into C++ code. And we follow a sort of convention in our flight software of having this kind of pattern where we can take stateful components and just directly express them as C++ classes in a way that looks kind of similar in different places when we look around the code. So if we have like a stateless component, like if you were doing like a block diagram description of a system, you could imagine something like a multiplier or an adder or something that's like a stateless component, right? Because the output is just a direct function of its input. Those we just use functions for in C++. So any inputs we pass into the function, and then you get an output by the return value. That's pretty obvious. And then any stateful component will usually make a class or a struct. They're the same thing in C++ with a name. And then for any inputs we have, we'll give those as functions that can get called to provide that input to the state of the class. And then for the outputs of a stateful component, we'll create a second type that's like an interface type in C++. I don't know if any of you have done C++ programming. I won't get too much into the details, but it's just kind of saying an interface. So this is like a class that you can define a type that follows this interface of defining functions for the outputs. And then if you use that stateful component, you define what you want to do to handle those outputs. So you would define a function called output x and say what you want to do inside to handle that output. Define a function called output y, say what you want to do when you handle output y. And then when you use the stateful component, sorry, I guess I labeled this stateful. I should have called this struct stateful and struct stateful user. Then you could use it by handling the outputs that it defines. Next slide. So to show two examples from our flight software, the safety module that we use, that's a stateless component because it's just there to check the collision risk on a given state estimate. So as our navigation runs and produces new state estimates, we'll hand those to our safety component, and that doesn't need to remember anything about past safety analyses. It just says, yes, no, passive safety violated. On the other hand, navigation, which is running an extended Kalman filter inside, that obviously has state inside, and so we use a class to store that state. And then we can input things like new attitude measurements, new GPS measurements, maneuver information from the controller, and so on, and similarly get outputs using this kind of navigation user interface type to say a new state estimate, and so on. Next slide. So that's like an overview of the flight software. I'll next talk about just a few aspects that I think are kind of interesting, unique aspects of the VISORS flight software, and stuff you might not always have to deal with in other flight software. So the first is the coordinated autonomy that we have to deal with in VISORS. Next slide. So VISORS, you really can't do without using onboard planning and onboard control. Whenever you're doing space missions, anything you can do on the ground, you absolutely should do on the ground. You should not run stuff on your spacecraft just for the fun of it. If you can get away with commanding from the ground, then you should. It gives you more flexibility and more robustness, less likely that you're going to lose your spacecraft to a silly bug. But for VISORS, the control accuracy that we need in especially science mode, centimeter level control requiring control every 45 seconds or 5 minutes is way smaller of a control horizon than the ground pass frequency that we expect to have, which is about every 4 orbits or so we'd expect to have a ground pass. Transfer mode we could maybe get away with doing from the ground, but even that is iffy. So this is just to say it's a hard requirement for visors that we have control being planned on board. Next slide. And at the same time, kind of a compounding factor that makes the flight software tricky for visors is that it's not just autonomy, but coordinated autonomy. So we actually need the two spacecraft to be in the loop with each other, in agreement on certain things throughout the mission. And some of those kind of requirements driving the need for coordinated autonomy is, for one, exclusivity of control. We don't want both spacecraft to be trying to maneuver at the same time. This is an autonomous distributed mission, but we're not trying to do distributed control algorithms or distributed optimization algorithms. We want to be able to use the control algorithms that can run on a single spacecraft, give a single solution that can then be implemented by the formation as a whole. But we're not trying to distribute computation kind of dynamically between spacecraft. We want one spacecraft to always be in charge, so to say. We need the spacecraft to take synchronized actions during observations. So at certain times in science mode, we'll actually need them to control their attitude simultaneously, or switch the status of subsystems in following a certain schedule that's synchronized between the two spacecraft. And amidst all of this, we also need the ability for the spacecraft to dynamically switch which one of them is the active one, which one of them is controlling, in order to be tolerant to certain faults. And so all of these together kind of create a potential for a messy painting of trying to get this coordination working between spacecraft in a safe way. So next slide. In order to do coordination between the spacecraft, we obviously need communication between the spacecraft. And so if you have a radio, cross-link radio between two spacecraft, you can think of it as both a sensor and an actuator, right, if you're transmitting or receiving. And just like any other sensor and actuator, it's important to understand the behavior and the performance of this sensor and actuator so you can model it correctly and design around it correctly. So for visors, we have a maximum cross-link range designed of 10 kilometers. But it's important to note that in wireless communication, a range is never a hard value and never something that means if you're within that, it works. And if you're outside of that, it doesn't work. It's more that range is specified in terms of sort of a bit error rate exceeding a threshold that you want to choose. And for example, if you say 10 to the minus 4 being your desired bit error rate at 10 kilometers, that would translate to an error in, like, say, a 1,000 byte message of around 50% at that bit error rate. And so if you're closer than that, you'll have a lower bit error rate, but it's never going to be 0. And so it's important to remember and design around cross-link communication never being completely reliable. You can try to pretend it's reliable by using retransmission, error correction codes. You want to do checksums and things like that, but at best, that's going to allow you to reject invalid messages. It'll never guarantee receipt of correct messages. Next slide. Go one slide back. Yeah, I don't need to go through all of this, but I actually wanted to just mention one thing that was kind of an interesting factor for the VISORS mission. So a bunch of things affect the signal-to-noise ratio of a crosslink antenna, but one ended up being a sort of large issue in the development of the VISORS mission because we were kind of left with this after the hardware had already been designed for VISORS. But it's important to be aware of these things. So polarization loss. Our patch antennas that we use on the VISORS spacecraft are linearly polarized. And so when you send an electromagnetic wave out, radio wave in space, depending on the type of antenna you can have, it can be polarized linearly or circularly. And if it's linearly polarized, that means the wave that you're sending actually has an orientation in space. And if you try to receive a linearly polarized wave with the linearly polarized antenna, you'll have effectively a cosine loss on, like, literally the twisting of the orientation of that polarization. And so, next slide, Ethan. A bit of the ways through development of the GNC software, I was going through the CAD and realized that on one of the faces of the VISORS spacecraft, the plus and minus X face, the two antennas are actually oriented 90 degrees away from each other. which means that in certain phases of the mission, we might expect to have lower signal to noise ratio on our crosslink antenna than expected. So this is just to say bit error rate and dropped messages is something we are even more sensitive to than we would have been otherwise. Next slide. So going back to these things of coordinated autonomy, we want to have coordinated autonomy in the presence of unreliable communication, which is the hard part. Next slide. So one of those things that I was mentioning, exclusive control in the presence of role switching, we want to guarantee that the spacecraft will never try to autonomously maneuver at the same time. If we did that, sort of all bets of like safety would be off. I mean, they wouldn't be off. We could try to design around it, but we didn't want to. We want to say, let's design our control algorithms to be safe, assuming that they're being carried out by a single spacecraft and not both spacecraft thinking that the other spacecraft is passive but accidentally maneuvering at the same time. So in order to try to solve the problem of a passive spacecraft being able to take control if it needs to, for example, if it thinks there's a collision risk, because that's an important design criteria of the VISORS software as well. Next slide. We use oh, my bad. Is that not there? Oh, you might need to exit the presentation mode and restart. Yeah, or maybe refresh. Yeah, great. So we use a protocol of requesting control from the active spacecraft. So if the passive spacecraft ever needs to, say, escape, or if there's, or if the active spacecraft wants to donate control because, say, it has a propulsion failure or something like that, we use an explicit handshaking protocol where any passive spacecraft that wants to become active has to actually explicitly request it from the other and say, get the active spacecraft to say, yes, I promise I'm going passive and I will not maneuver anymore. You can become active. And in that case, we can become active. A challenge with this is in the presence of unreliable communication. Next slide. You can imagine, we can ask the question, and you have to ask the question, like, what happens if one of these messages gets dropped? So if the passive spacecraft that wants to do an escape because it thinks there's a collision risk requests control from the active spacecraft, and then the active spacecraft yields, the passive spacecraft, let's say it never gets that message. Maybe the crosslink system reboots or something, or that individual message gets dropped. We can try to retransmit, and we will keep trying to retransmit, but let's just say in the worst case, we never get any of them. Neither spacecraft can really do anything here because spacecraft 1 doesn't know that the message was dropped necessarily. I mean, there's just no way to know. And spacecraft 2 doesn't know that the message was attempted to be sent. So both spacecraft kind of have to stay passive. And this is very similar to, next slide, the two generals problem. I don't know if anyone's heard of the two generals problem, but it's a sort of thought experiment in communication theory, where if you have two generals on opposite sides of a city trying to attack, and they need to coordinate their attack in order to have a chance of success, they can try to send messages back and forth to agree on the time to attack the city, but neither of them can really be sure that the other one is going to attack at the same time, because let's say the first one on the left sends a message saying, I'm going to attack tomorrow at 8 a.m. If the second general doesn't receive that message, the first general should not attack, because they would lose the battle if they attack and the second general is not there. Meanwhile, if the second general sends a confirmation back saying, yes, I got your message, then he doesn't know that that confirmation got back to the first general. So the first general may still not attack, and so the second general should not attack. And so you could do this back and forth forever and never really get to a resolution. And in general, this problem is unsolvable. So for VISORS, next slide, we just have to accept the possibility that both spacecraft might go passive if one of these kind of handshakes fails. And we try to mitigate this by doing retransmission of messages, of course. But in the worst case, we just have to know and design around the fact that both spacecraft might go passive. And there's no magic solution to that. There's no way to get around that. And if that happens, we resolve it by intervention from the ground. Next slide. Other thing we do, try to move through this one faster. In science mode, we obviously have to sequence a lot of events relative to these observations that we're taking. So every time we come around once per orbit and we do an observation, before each observation time, there's various other events and actions we need to take. So we have to do an attitude slew, we have to turn on and off other subsystems, we have to send commands at times offset to the intended observation start time. And so when we originally wrote the software, before we really were paying much attention to the cross-link communication, we just said, okay, the active spacecraft knows what's going on, it's planning the maneuvers, doing the model predictive control up to the observation time. So it will just fire these events. And if anything has to be done on the passive spacecraft, we'll just tell the passive spacecraft to do it, right? Because one spacecraft is always in charge. So the spacecraft in charge can always do it. And the problem with that is that if you have delays or drops in any messages, and some are more critical in timing than others, you'll have unnecessary delays. Maybe, things might be delayed by several seconds, which for some things is fine, but for an observation window that's 10 seconds long, you don't want to delay the start of the observation by 10 seconds on the other spacecraft, or by a few seconds on the other spacecraft. So ultimately, we switched to a design, next slide, where the observation time is committed to well in advance. It's committed to at the start of each orbit. So we do one observation per orbit, and that time is locked at the start of that orbit. And then that time can be sent to the other spacecraft well in advance. They both have GPS receivers, and so their clocks are synchronized to GPS time, and they can both independently take their actions relative to the observation time that they both agreed on. In hindsight, this kind of design is something pretty obvious that you would just do the first time, but the point of this is just it's something that you don't really think of until you have to consider it, and this reliability in the presence of unreliable communication is an important part of an autonomous distributed space mission. Next slide. Let's see, computational efficiency. I'll try to summarize some of this. Basically, matrices can get really big. Try to minimize the time you spend doing multiplications of really big matrices. Often you'll have either sparse equations, so you only are using small parts of the matrix, or sparse vectors or sparse matrices, and you can actually encode that into the structure of your code. So one place we've done this is in the navigation component for VISORS. We've started using a lot of sparse math in our Kalman filter navigation updates. And so this measurement update, scalar measurement update, years ago was taking the majority of computation time in the GNC software. And over time, we've kind of transformed it to take advantage of the fact that, next slide, this vector C, the sensitivity vector for scalar measurement, tends to only have a few non-zero elements. So next slide. Next slide. If you skip all the multiplications by 0 and skip all the multiplications by 1, because you know the answers of those are going to be ahead of time, and skip additions with 0, you can end up skipping a lot of the computation in a large matrix. And so if you have this big covariance matrix, you actually don't need to do a lot of the work to loop over it. And so over the last few years, we've been able to bring down the runtime of this algorithm a lot, which has actually enabled us to have a higher measurement frequency and get us better accuracy of navigation. So sometimes being able to shave off runtime will actually enable you to fundamentally get better accuracy, better performance out of your algorithms, not just use less CPU time. But it also has the benefit of enabling faster simulations during development, so you can iterate fast. It's nice too. Next slide. Similarly, for memory use, sometimes matrices are just so big that they won't even fit in the memory that you have on a spacecraft microprocessor. So one of the biggest matrices we have in the VISORS flight software is used for maneuver splitting. That magnitude constraint Mason was speaking about earlier, where we need to take large maneuvers and split them into many small maneuvers. And the default way we do this is by solving a linear program. And it tends to be that the matrix G for this linear program is really large, but has a mostly diagonal or block diagonal substructure to it. And so we can use a sparse matrix representation, and luckily the optimization software we're using, ECOS, supports problems being specified in this sparse representation. And so we don't even want to make the matrix in the first place. Like, don't even allocate the memory for it. Don't even build it in the first place. Just directly create the sparse representation from the problem variables we have and pass that straight to ecos. And so that ended up causing I guess you can see in these diagrams on the top right a kind of memory consumption of the GNC software. In some cases, brought us down by like an order of magnitude or more of memory consumption, which was good because previously we were crashing our software because we were exceeding the amount of memory we had on board. Similar kind of thing happened for the Star Fox mission that Justin Kruger spoke to you guys about, of angles-only navigation. They had some issues getting their software to run early on in the mission, also because of excessive memory use. So in some ways, memory use is the real killer more than runtime, because if it's just runtime, you'll get the right answer eventually. It's just slow. But if you run out of memory, there's nothing that your computer can do. So next slide. You can skip this slide. That's just on the sparse representation. All right, the last performance thing is write good code. So next slide. I don't know if any of you guys have heard this quote before. Premature optimization is the root of all evil. If I were there, I would say show of hands if anyone's heard this quote before. But this is often repeated in software engineering to mean, don't optimize something before you know it's actually a problem. And that's true and a good point, but I have mixed feelings about this quote because often it's thrown around as an excuse to not worry about performance at all, which I think is the wrong way to go. So I have a new quote, which is next slide. Don't do things the slow way if you can just as easily do them the fast way, Toby Bell. And so some of the general rules of thumb that we follow in the VISORS flight software. Next slide. We avoid dynamic memory allocation. We used fixed size vectors in our code where we can. Pass large structures by reference rather than copy. Store frequently accessed data close together. That helps hardware cache it better. Keep your data small. That'll also just help you get more mileage out of whatever caches you do have on your CPU. Most data structures, simple linear arrays are the best. Even if you have to do a linear search through an array, if that array is small, it'll almost always be faster than a quote unquote O of 1 fancy algorithm that you might learn about in a CS class. And build indices over frequently searched through data. And so we just kind of follow these rules of thumb a lot of places, try to avoid doing nested for loops and do these things even without having to measure, and you'll be in a better spot than if you say, oh, never worry about performance until it's a problem. Next slide. Okay, only a few minutes left. I won't go into all the detail here, but testing and simulation. The next slide. Just wanted to give a sense of the way we've done simulation in the VISORS flight software. On the whole, my opinion is that simulation is as important as the flight software itself. I think if you're working on a flight software project, you should be spending as much effort on your simulation tools and environment as you are spending on building your actual flight algorithms. So for VISORS, we've been using a simulation environment that has been co-developed along with the flight software for the last 3 years. And it operates by directly operating on the compiled flight software. So that shared library that we'd be delivering to Georgia Tech, we compile that, and then we can run it in simulation using all the inputs and outputs that Georgia Tech will actually be using. But we can run it faster than real time, 100% deterministically. If we need to step through it in a debugger, we can. And I think this has been a very invaluable part of developing high fidelity, high performance, complex flight software for VISORS. Let's see, maybe we can just flip through these. Next slide. No, I won't talk about that. Next slide. I just don't want to keep you guys past the end. Virtual interface. Yeah, this is just emphasizing the fact that you want to design the interface of your flight software in a way that will let you use it both in flight and in simulation, right? So you can very easily write software that is hard to simulate, that's hard to test because the interface is not well defined. right? So if you write a piece of software that's going and reading from lots of files on your operating system, on your file system, it's going and opening network connections to a bunch of other things that it wants to communicate with. This can be very hard to simulate because it's not exactly clear what the interface to your software is. Like all of those are kind of points where information is entering and exiting your software. You want to have a really tight grip on all of those. And so for the VISORS software, the interface is something we've always controlled from the beginning really tightly. It doesn't do any implicit networking. It doesn't do any implicit file access. Every input and output is very clearly defined by function calls in our flight software. And so Georgia Tech uses that, but we also use that in our simulation, and we know that it'll behave exactly the same way every time. Next slide. Ultimately, we put all this stuff in a simulation process. So we put our flight software, ground software in a simulation process, run it deterministically, and get a log of everything that happens. Next slide. Bunch of environment models. I'll just call out one of them. Next slide. All this is normal. I'm sure you guys have done like sensor and actuator modeling in the simulations you guys write. But of note for VISORS is because we rely so much on the high precision differential GPS, part of the biggest investment we've made in simulation is having a really good GPS constellation simulation. And so we modeled the orbits of all 31 active GPS satellites and model the behavior of our GPS receivers down to the binary protocol that they speak. So we have a software model of everything that our GPS receivers do, depending on the states and orbits and noise that we expect to get from each individual GPS satellite. We validate this against GPS Signal Simulator, which is a commercial product you can buy that simulates the analog signals from GPS receiver, or a GPS antenna that you can feed into a receiver, and run those on real Novatel receivers. And so we can improve our simulation based on the data that we get from doing that. Next slide. So once you do all this, you can do a bunch of cool things like running full system, full mission Monte Carlo simulations. So we can take the literal compiled flight software, like the thing that you would go put on the spacecraft flight computer, and run it for 6 months of mission time on your desktop, and run that in a matter of minutes. So you can run a simulation on your computer for 10 minutes and get 6 months of, I mean, maybe not 10 minutes, maybe you run it for 20 minutes or 30 minutes, but you get 6 months of mission duration time, including everything that your flight software was going to run during that time. And you can do this in Monte Carlo, and you can collect statistics over how sensitive your software is to different parameters, not just at the level of like a pre-implementation or prototype, but on the literal final product that you're ready to ship. So that's really valuable. Next slide. I skipped the event-driven part. I'll skip this too. Well, I'll just mention this. No, go back one slide. Another thing that's been useful for VISORS is we don't just do continuous quantity simulation in our simulations. So we're not just focused on the kind of the dynamic system, the dynamical system, and like the integration of dynamics. We care a lot about the discrete behavior of systems as well. And that allows us to model things like delays in the delivery of packets between our two spacecraft, or dropped packets between our spacecraft. And so our simulation operates in a kind of hybrid between discrete event simulation and continuous dynamical simulation that is usually used for like orbit or attitude dynamics. And so it's been very nice to have that hybrid where we can get really nitty gritty with the microsecond level timing of things and use like sample noise distributions on the timing of events that we want to simulate and see, can we cause our flight software to crash if the crosslink is delayed or if the crosslink gets dropped, for example. Are there bugs that we find? We can fix those. Next slide. And then having had a good software simulation, we can sub out components of the software simulation with hardware. So we've done processor in the loop simulation, which is where you take the simulation all still runs the same way. You don't necessarily run it real time. You're just swapping out the code that you would have normally run on your simulation computer to have it run on a different computer. And so we've done this on a few different processors. We've done it on a Raspberry Pi Zero, and we've also done it on a Xilinx Zinc 7000, which is the flight computer that will actually run in the VISORS mission. but we can run the same simulation, but run all of our flight algorithms on this external processor, which lets us make sure that our algorithm is actually robust and not relying on any kind of features of the software or behaviors that only show up on our like desktop computers when we develop. All right, let's skip through the rest. I started going long. Yeah, let's just skip. But again, I would just say simulation is very important. You can go back one slide, Mason. This is my, if I can send a message to everyone. If you're trying to build flight software, and importantly, you're trying to do state-of-the-art stuff, trying to do new things that people haven't done in space before, invest in your simulation. There's no really other way to know what your software is going to do ahead of time, unless you invest in good simulation. So spend at least as much time on the simulation as you spend on the flight software, and it will help you ultimately go faster in the long run. That is all. Thank you for your attention. Oh, you can ignore this. Oh yeah, you should go to the next slide. That was our original title slide.